In this video, we're going to compute the inductance per unit length of a coaxial cable by integrating the energy density. So the main idea of this technique is that we can write down the magnetic field energy density for any particular region in space in terms of the magnetic field magnitude in that region. So this is the formula we derived in the previous video. Little u, that's the energy density or energy per unit volume, is 1 over 2 mu naught times b squared. So if we can figure out the magnetic field in a particular region, we just have to integrate the energy density to get the total energy stored in the magnetic field in that region. Next, we're going to relate the energy in our conductor configuration to the inductance by using the formula we derived for the energy in an inductor. And that's big U for the total energy is equal to 1/2 Li squared, where L is the inductance. Now, because this coaxial cable goes on forever in both directions, we actually want to compute the inductance only for a finite length of little l along this thing. And then we can talk about the energy per unit length related to the inductance per unit length. So that energy per unit length is going to be I squared over 2 times the inductance per unit length. And this means the inductance per unit length is going to be 2 over I squared times the energy per unit length. So that's the main plan for this problem. We're going to compute the energy stored in the magnetic field over a length of little l along the cable, and then solve for the inductance per unit length as 2 over I squared times the energy per unit length. Now I have to explain a quirk of the setup here because in the past our basic coaxial cable has been a thin central wire surrounded by a thin foil. So in other words, that central conductor was infinitesimally thin. And the issue there is that the thin wire limit causes the magnetic field to spike to infinity at r equals 0, and that's going to blow up our energy integral. So we had to be a little more realistic with this cable and give the central conductor some thickness, and that's a radius of a. But keep in mind, for a realistic coaxial cable, a is going to be very small compared to the outer radius b for the conductive foil on the outside. And we're actually going to use that fact to perform an approximation late in our calculation. So keep in mind that this picture is grossly exaggerating the thickness of the inner wire, just so we can visualize things more easily while we compute the energy integral. And one last thing I should mention, we're going to assume the current density is uniform within that central conductor. So we use a simple uniform current density of J in there. That current density is just current divided by cross-sectional area, so we can say that J is I over pi a squared. So the first order of business here is to use Ampere's law to quickly compute the magnetic field in every region along this little length of L. So we've got 3 regions. There's a region inside the central conductor, between the two conductors, and outside the outer conductor. And these are all Ampere's law applications that we've handled before, but I'll run through the calculations real quick as a refresher, and as I do that, I'll post links to the detailed prior calculations. So let's start inside the inner conductor, and we've put an Amperian loop of radius r in there. If we stick the thumb of our right hand in the direction of the current, the magnetic field circulates around circumferentially in the same direction as the curl of our fingers. And so we write down Ampere's law. The path integral of B dotted into dl along this loop is equal to mu naught times the current enclosed by the loop. And B is always going to be parallel to the path increments. Those are the dl's, so the dot product is going to be trivial. That means the dot product reduces to B times dl. And the magnitude of B is constant along the loop by symmetry, so we can pull it out of the integral. And then we find ourselves just integrating dl itself, which is the circumference 2 pi r. So on the left-hand side, I've done all that stuff to decompose the integral. We pulled the B out, we integrated dl, we got 2 pi r. And on the right side, I've computed I enclosed. Now remember that J, the current density, is the current per unit area. So if I just take that and multiply by the area of the Amperian loop, I get the current passing through the loop. So that's going to be J times pi r squared. So we go ahead and solve for B here. And all I did there was just divide both sides by 2 pi r. And now we're going to clean things up a little bit. We'll cancel a factor of pi and a factor of r. And we arrive at this expression for the magnetic field inside the inner conductor. That's mu naught J times r over 2. But we really want to express this in terms of the total current flowing in that conductor. So remember, J is I over pi a squared. So we make that replacement and we arrive at our final formula for the magnetic field inside the central conductor. That's mu naught I times r over 2 pi a squared. So note here that magnetic field is linearly increasing from the center out. So next we're going to look at the region between the two conductors. So we set up an Amperian loop that has a radius bigger than A. And again, we're going to set up Ampere's law. And all the same arguments about the magnitude and direction of B are going to be the same. The dot product is trivial, the magnitude of B is constant, we can factor it out of the integral, and we end up just integrating dl and getting 2 pi r out of that. And notice on the right-hand side, well, the enclosed current here is the entire current I. So this is a classic result. We just get B times 2 pi r is equal to mu naught I. And our magnetic field result is very familiar here because it's the same thing you get for just an isolated thin wire. It's just mu naught I over 2 pi r. Now finally, we look in the third possible region, which is outside the entire coaxial cable. And this time the result is trivial because the net current passing through this loop is actually 0. We have I pointed to the right and I pointed to the left. So with an enclosed current of 0, we're guaranteed to have a magnetic field of 0. And we're done finding the magnetic field in all 3 regions for this conductor. So we just make a note on the 2 non-trivial magnetic field results. And now the next order of business is to determine the total magnetic field energy along this length of little l. So we have to split the calculation into 2 pieces for the 2 different fields. Just remembering that outside the entire coaxial cable, B is 0, so that contributes nothing. And we're going to start with the inner conductor. So there's our basic formula for the magnetic field energy density. It's 1 over 2 mu naught times B squared. And we just plug our known magnetic field into that. And we have to square that magnetic field. So things are getting a little bit messy here. And so I've squared all that stuff and canceled the factor of mu naught and then combined the constants in the denominator. And we get a magnetic field energy density of mu naught I squared R squared over 8 pi squared A to the 4th. Now, since the magnetic field is changing with R, our magnetic field energy density is also changing with R. And that means we need to split up the volume inside this conductor into thin cylindrical shells along which the magnetic field is constant. So there's a shell of radius r and length little l, and inside that shell wall, the magnetic field has a single unique value for that value of r. This allows us to find the energy contained within the shell wall by simply taking the magnetic field energy density and then multiplying by the incremental volume contained in the shell. So there's a general expression for an increment of field energy. I wrote that as d big U. So that's an increment of magnetic field energy captured within this thin shell wall. And now we have to put in the details about the energy density and the volume of that shell wall. Now to get dV, the volume of that shell wall, we're simply going to slice the shell lengthwise and unroll it into a rectangular slab. And the length of that slab is L. The width corresponds to the former circumference before we unrolled it, so that's 2 pi r, and the thickness is dr. So this gives us dV equals 2 pi r L times dr. So we sub that into our expression for d big U, and there's a couple of things we can clean up here. We can cancel a factor of 2 and a factor of pi, and combine our r's into an r cubed. And so we've done all that stuff and moved all the constants out in front, and then we have an r cubed dr. So now that du is phrased entirely in terms of r, we're ready to sum up all the du's by integrating. So there's our most basic statement of what an integral does. It's a summation device for adding up infinitely many infinitesimal contributions. So then we sub in the details about du, and we have to pick some limits of integration here. Well, we're integrating as r goes from 0 to a. And as I write this down, I'm just going to pull all those constants out in front. So now we have mu naught I squared little l over 4 pi a to the 4th times the integral from 0 to a of r cubed dr. Fortunately, this integral is trivial, and it just gives us a 1/4 r to the 4th, which is then 1/4 a to the 4th after evaluating across the limits. So now we can clean a couple things up, canceling the a to the 4ths and combining the 4's in the denominator. And we get mu naught I squared L over 16 pi. Now there's just one more thing to do to this. We're going to divide both sides by little l to get an energy per unit length out of it. So we get for our energy per unit length, we get mu naught I squared over 16 pi. And we'll just store that guy over there on the left. Now we shift to the energy calculation between the conductors. So again, we start with the basic magnetic field energy density formula. That's 1 over 2 mu naught times B squared, and we just sub in our magnetic field, and that was mu naught I over 2 pi r, and remember we have to square that. So we just clean it up by squaring everything and then canceling a factor of mu naught and combining the constants together. And there's our energy density. It's mu naught I squared over 8 pi squared r squared. And again, we need a thin cylindrical shell in order to calculate an energy increment in this region. And the whole point of that is that the thin shell wall is located at one specific value of R, and that allows us to get the energy contribution by just taking energy density and multiplying by the volume of that thin shell wall. So we write du is little u dv, that's just energy density times volume. And there's nothing new about how the dv turns out. We just slice this thing and unroll it and we get the exact same expression. So in this expression, I've just replaced dv with 2 pi r L dr. Now there's a little bit of cleanup work to do. We can cancel a 2 and a pi and a factor of r. And when we're done with that, we end up with all these constants out in front, mu naught I squared L over 4 pi. And then we have our variable pieces. We have 1 over r times dr. And at this point, we're ready to sum up all these energy contributions. So u is just the integral of du, and we plug in all the details for du, moving the constants out in front of that integral, and then remembering that we're integrating as r goes from a to b this time. So again, there's nothing difficult about the integral. 1 over r just integrates to the natural log function. So the result of the integral is going to be natural log b minus natural log of a, but then we can use log properties to write that as natural log b over a. So I end up with mu naught I squared L over 4 pi times the natural log of b over a. Finally, we're going to express an energy per unit length out of this by dividing both sides by little l. So there's our second energy. So now we're ready to take our energy per unit length in these two different regions and use it to find the inductance per unit length of the cable. So remember, we turned around the formula for inductor energy to obtain a formula for the inductance per unit length in terms of field energy per unit length. And it turned out to be this. The inductance per unit length is 2 over I squared times the energy per unit length. So now we can just put in the sum of our magnetic field energies per unit length. And note there, the term on the left is the contribution from inside the inner conductor, and the term on the right is the contribution from the space between the conductors. So we'll clean things up a little bit by canceling the I squared and canceling a factor of 2. And we arrive at our final answer for the inductance per unit length. So it turns out to be mu naught over 8 pi plus mu naught over 2 pi times the natural log of b over a. So you might notice a discrepancy between this and the formula most commonly stated on the internet. And the reason why is that most references don't include that term for the inside of the inner conductor. So what we're going to do is make an approximation. Remember, A is going to be very small compared to B. And this means B over A is a rather large number. And then natural log b over a is a rather large number. So that term out in front, the mu naught over 8 pi, is going to be negligible. So I went ahead and put an approximately equal to sign on this. And there's our classic result for the inductance per unit length of a coaxial cable, mu naught over 2 pi times natural log of b over a. In the next video, we're going to calculate the inductance of a thick toroidal coil using this same technique of computing the magnetic field energy density when a current of I runs in the coil. I'll post a link to that video at the upper left, and I'll see you there.